Hello, I'm Rodrigo Avalos, and together with Professor Jorge Lira from the Federal University of Ceará, we will be delivering an advanced course entitled The Einstein Constraint Equations in the following Brazilian Colloquium of Mathematics. In what follows, I will give you an overview of the contents of this course. The layout I'm going to show you next is going to be a close version to the written version of the course. And the first chapter is going to be an introduction to general relativity intended to bring everyone to the same place for the following chapters. The first section is going to introduce some rudiments concerning Lorentzian geometry. And the first objective is to introduce the Einstein equations, which are given by this equation 1. Here, G bar stands for a Lorentzian metric posed on some space-time manifold that we're going to take of this form, M cross R, where M stands for n-dimensional manifold. The left-hand side of these equations are the well-known Einstein tensor, and the right-hand side stands for the energy momentum tensor field, which might depend also on some collection of physical fields here collectively denoted by this field psi. The first objective here is to introduce some intuitions about these equations by presenting some examples and classical constructions. But then the idea is to move on to the initial value formulation of the theory. As we will see, the idea here is to be able to produce spacetimes by evolving appropriate initial data sets. An appropriate initial data set we will see that consists on a Riemannian manifold Mg equipped with some symmetric 0-2 tensor field that plays the part of the extrinsic curvature of this manifold as embedded in spacetime. And the problem is to find precisely an embedding of this initial data set into a spacetime which satisfies the Einstein equations for some prescribed form for the matter fields. The idea here is that if K is going to play the part of the extrinsic curvature of some T0 slice, then we know from the Gauss-Kodazzi equations that G and K must be related. And this is expressed via this condition 2, where the first equation is basically a trace of the well-known Gauss equation, and the second one is the Kodazzi equation. The right-hand side of these equations are the energy density and the momentum density induced by the energy momentum tensor field. And they, again, depend on our choice of matter fields. So these equations become necessary conditions for the problems to be well posed. It is also a remarkable fact that these equations, in most cases of interest, are also sufficient conditions for the problems to be well posed. And this poses these equations right in the center in the analysis of the evolution problem in general relativity. And this course will be devoted to the analysis of these equations. We will be interested in producing solutions and analyzing properties of solutions, global properties, and so on. We will end this chapter by introducing black hole solutions. The moral of this section is to introduce certain characterizations of black hole solutions via initial data sets in the form of boundary conditions for the initial data sets. This will be used in the upcoming chapters. The second chapter will concern an overview of classical results, and we will start with the so-called conformal method. This is the best known method to produce solutions of the constraint equations, and the idea is here to split the geometric data GK in this form here, where the red quantities are the freely prescribed quantities, and we try to solve the equations then for a conformal factor, and this part of the trace-free part of the extrinsic curvature. Here we're prescribing the conformal class of the metric, we're prescribing the trace part of the extrinsic curvature, that is the mean curvature, and some other part of the trace-free part of the extrinsic curvature. Using this decomposition into the equations 2, we see that the set of equations, which are geometric equations 2, gets translated into a set of geometric PDE equations here given by this system. Here, this is the Riemannian Laplacian on the metric gamma, and this operator is called the conformal killing operator. Both of them are linear elliptic operators. And then the idea from now on is going to be to analyze existence or non-existent results for solutions of these kind of systems, and also properties of the solutions. And the first step here is to realize that under some simplifying assumptions, this system can be significantly simplified. For instance, if we impose a constant mean curvature condition that we will call from now on a CMC condition, then the interaction between these two equations via this term is killed. And then in particular, when this J scales in some appropriate manner so as to compensate for this conformal factor, this equation completely decouples. And in that case, the core of the analysis relies in analyzing the associated Lich-Nervix equation, which is this first equation, in detail. So the next section will be devoted to this kind of analysis. So the idea is to first analyze Lich-Nervix type equation on closed manifolds, and we will refer to a foundational paper by James Eisenberg, which basically can be summarized in a table of this form. So the idea is that depending on the Yamabe class of our metric and on whether the mean curvature and the TT part of our initial data set are 0 or not, we can completely classify the vacuum CMC solutions. We will present some updates of these results, basically extending these results to the cases where we have still a CMC condition, but we have matter fields, and also to low regularity settings. Then the idea is to move to non-compact settings. So the case we will be most interested in is the asymptotically Euclidean case. These are non-compact manifolds that have a particularly simple asymptotic structure at infinity, and they serve as models for isolated gravitational systems. The objective will be to translate the kind of results and classifications I just commented above to this setting, and in particular we will follow papers, foundational papers like these two, where the first one in particular incorporates boundary conditions for our problem that model black hole initial data. We will end this chapter by introducing some linear stability analysis. This is a classical topic, but we have still ongoing research in this area up to this date. And this is also related to the possibility of giving a manifold structure to the space of solutions of the constraint equations. This will be detailed in the written version and commented also during our video lectures. In chapter 3, the idea is to move to the analysis of the Einstein constraint equations outside the CMC condition. This is recent progress, and the first thing to do clearly is to analyze the near CMC case. This allows us to appeal to certain implicit function arguments. And then the idea is to move towards removing the CMC condition completely. We will first do this by reviewing this foundational paper by David Maxwell, where he is able to produce such classifications with freely prescribed mean curvatures in the vacuum case. And for phenomenological sources, we have this other foundational paper by Michael Holtz and his colleagues. And we will present this, and further, the idea is to end this chapter commenting on a recent paper written by myself and Professor Jorge Lira concerning these Einstein type elliptic systems, which are systems of elliptic PDEs that look roughly like this. These are very broad generalizations of the kind of systems that I showed you above. Here, these Y fields, they are sections of special vector bundles, and this model the conformally formulated constraint equations, also coupled to further constraints that may arise, for instance, when we couple the constraints with matter fields such as Young-Mills and, for instance, the case of electromagnetic fields. In those cases, we get larger systems, and in general situations, these systems are completely coupled. They don't decouple even under CMC conditions. So we will present a detailed analysis of these very general systems that generalize the above settings. Finally, the last chapter is going to be devoted to gluing constructions concerning the Einstein constraint equations. Here, the idea is, say we have two vacuum initial data sets, and we want to produce a new solution on the connected sum here. And the idea is to respect the original ones outside the gluing region. We should picture this as either having two disconnected solutions and we want to join them with an egg, or maybe having just one solution and taking 2 points and we want to join neighborhoods of those points with a handle. And this can be done, for instance, via a foundational paper due to James Eisenberg, Rafe Maceo, and Daniel Pollack, that is called the IMP gluing. Here, what we get is this connected sum construction, and we get that the solutions outside the gluing region are close to the original ones. A further development in this direction is given by trying to produce localized gluings which actually agree with the original solutions outside the gluing region. This is done, for instance, following foundational papers by Crucial and Delay and also by Corvino and Shen. This material will be presented within 5 lectures, and so probably not all the above material can be covered in the video lectures, but the idea is to cover most of it, and then for the audience to be able to complement these lectures with the written material. And the objectives are to introduce a broad audience of researchers interested in this interface between different geometry, geometrical analysis, and physics to current research in mathematical general relativity. The prerequisites are going to be differential geometry, Riemannian geometry, and preferable some PDE experience. And by that, what we mean is that within the video lectures, probably we will not be able to cover most of the PDE background, but certainly in the appendix, in the analytical preliminaries, we will cover it in the written version so that everyone can follow the video lectures following the appendix. Finally, for any kind of comments, you can contact us in our emails, either by me or Jorge Lira. And we are grateful for the organizing committee of the colloquium for giving us the opportunity to deliver this course, and we hope to see you all in the colloquium.